In the previous video, we set up a basic isometric tile map in Unity. In this video, we'll extend the concept to include multiple layers. One layer for buildings and another layer for collision. We'll rename our original tile map Tiles, and then we'll create another isometric Z as Y tile map and rename this one to Buildings. Under the Tilemap renderer component, let's change the mode to individual as we did before, and then also change the order in layer to 1. This will place the buildings layer above the tiles layer. Now let's choose the red brick tile from the palette. We're going to paint on the tile map again, but this time we need to change the Z value so that it looks like it's raised up like a wall. To do this, we can pull up the bottom panel on the tile palette. Here we'll be able to see that all our previous tiles had been painted at a Z position of 0. But we can use the plus and minus keys to change this Z value as we're painting. This will allow us to bring the tile up above the ground or even below the ground. The blue square shows you the current Z and the white square shows you the 0. Now let's use the filled box brush to paint a simple building. Okay, that covers the basics of adding multiple layers to an isometric tile map. We are going to come back to this concept in greater detail, but it would be really nice to be able to move the camera around the scene. So let's write a simple camera controller script that will allow us to explore the world. First, we'll create a directory in our assets where we can store all of our scripts. Then inside that directory, we'll create a new C# script called camera controller. Now let's open that script in our editor. What we want to be able to do is pan the camera and also zoom in and out of the map. We'll write the panning code first, and then the zoom effect will actually be quite similar. We'll start by defining two public variables that we can use to store the speed of the pan and the zoom. They are both float values, and we're defining them as public variables so that they're available in the Unity interface. Everything else we'll need to do in the update function. Here in the update function, we'll define two float variables that will store the change in the camera's position. The first variable we'll call dx, and it will represent the change in the x position. The second variable will be called dy, and will represent the change in the y position. We'll calculate this change by multiplying the pan speed, the delta time, and the input values. The delta time is the amount of time that's passed since the last call to update. It's important to get an accurate measure of this time in order to get smooth gameplay. Once we have these changes stored in these variables, then we simply have to translate the camera's transform component by these values. Unity provides a direct reference to the camera in every script, so we can call the translate method directly on the camera transform. The last thing we have to do is attach this script to the camera, but as you can see here, the class did not correctly get named camera controller, so I have to update that real quick before we attach it. And now we can simply drag the script onto the main camera in order to attach the component. And finally, we can run the game and test it out. Alright, it looks like the camera controls are working correctly. It is a little laggy, but that's just because of the screen recording. Okay, let's work on setting up the zoom feature now. We're going to rename one of the input axes to better fit our game. We go back to the project settings under the Edit menu, and we choose the Input Manager section. We're going to redefine the Fire 1 axis to be our zoom axis. We'll set the positive button to be the letter E, and the negative button to be the letter Q. These are conveniently placed next to WASD, so we can pan and zoom easily with our keyboard. Later on, we can add more mouse controls for even more flexibility. I'll also set the axis to be a third axis scroll wheel. That's usually how zoom is mapped to input. Now if we return to our camera controller script, we can access the zoom axis exactly how we got the horizontal and vertical values earlier. The only difference is that we'll multiply by the zoom speed this time. Finally, we need to apply this variable to the orthographic size of the camera. This changes the size of the viewing area for the camera, which creates a zooming effect. We will also clamp this value so that the user can't zoom excessively and mess up the display of the game. Alright, that should be all we need to get the zoom feature working. Let's go back to the game and take a look. Alright, it looks like everything's working. It can zoom in and out, and it has the maximum and minimum restricting its movement. Now that we got the camera controller working correctly, let's put the character into our scene. To get started, let's drag one of the character sprites into the scene. We'll rename this sprite to Character. We need to set our character's order in layer to 1, which is the same as the buildings layer. This will bring our character above the tiles. And we also need to set the sprite sort point of the sprite renderer to pivot instead of center. This is so that the sprite gets sorted based on where its feet are and not the center of the sprite. We're going to create a new script called Character Animator. We'll open this script in the editor. We need to define 8 public variables. These hold the character's 4 walking animations and the 4 idle animations. Each variable is going to be an array of sprites. We can now return to Unity. First, we'll attach the script directly to the character, and then we'll assign the correct images to these sprite arrays. We can lock the inspector to make it easier to load all of these images into these arrays. We just need to match each collection of images to the right sprite array of frames. Now let's return to the character animator script. We need a few private variables to control these animations. We will define one more sprite array to hold a reference to the animation that is currently playing. We will also define a variable to hold the sprite renderer component of our character. We use this reference to control the active sprite of our character. Let's also assign this reference in the start function using the getComponent function. Now let's define 3 variables that will control the timing of the animation. Timer is a float that will count up until the next sprite transition. Our animation will be a series of images, and we store the position in that series in the variable frame number. Finally, we define a frame rate variable that sets how long each sprite should be displayed before moving to the next one. We are going to display each frame for 1/10 of a second. We now define a new method called updateFrame. In the method, we add the delta time to our timer variable. And then we use an if statement to see if we have to move the animation to the next frame. We test to see if the timer is greater than or equal to the frame rate. If it is, then we reset the timer, increase the current frame number, and then look up the correct sprite in the current frames array. We can now test the animation code by setting the current frames variable to one of the animations. We can set it in the start method. We'll set it to the walk right frames. Finally, we need to actually call update frame in the update method. Okay, let's run the project again and see what this looks like. Alright, it looks like it's working correctly. We set it to the walk right frames and it's clearly displaying the walking right animation. We now want another method that will allow us to play any of our animations. We'll first create a new script that contains an enumeration to hold all the different animation types we'll be using. We create a new script called character animation type. We can delete all of the generated code that comes in this file and simply define a public enum that contains a name for each animation. We're now ready to write the play animation method. This method has one argument with the enum type that we just defined. To start this method, we reset the variables that track the timing of the animation. We need to define one more private variable to hold the current animation type. This allows us an easy way to track what animation is currently playing, because sometimes it affects the next animation we will choose. At the top, we'll simply define a new variable that has the enum type we created earlier. This is the variable we just used in the last line of the play animation method. To finish the play animation method, we need one large switch statement. It switches on the chosen animation type. It will go through each case and assign the current frames sprite array to the correct frames for this chosen animation type. Because update frame relies on the current frames array as well, this now allows us to play any of our animations simply by calling play animation with the matching animation type. Let's test this by replacing our direct assignment to current frames in the start method with a call to this new method, play animation. Okay, it is definitely playing the walk down animation, which is the one that we set it to using the play animation method. We'll end this video here, but in the next video we will begin adding behaviors to our character. We will start with a script that lets the character choose a random direction to walk.